Hi everyone, my name is Neil McIsaac. I'm a Microsoft Technical Trainer within Worldwide Learning here at Microsoft, and I'm responsible for providing technical skilling on Microsoft's cloud technologies to our top enterprise customers. I've been in the IT industry for over 30 years now, and I've been working in the AI and business intelligence space since around the early 90s. I've also been supporting Azure since 2008, which is about 2 years before Azure was generally available to the public. And with that, I'd like to welcome everyone to this course on designing and implementing a data science solution on Azure. The target audience for this course are data scientists that want to learn how to build, test, and operate their own AI models using the Azure Machine Learning Service. So our focus will really be about using the service. The expectation is that everyone taking this course is already familiar with the fundamentals of developing machine learning models. For example, you should have some experience working with frameworks like scikit-learn, PyTorch, TensorFlow, those type of things, and are familiar with working in Python to develop and manage machine learning models. That being said, we get a lot of people that are not data scientists attending this course, and that's absolutely okay. I would, however, highly recommend that you check out our AI 900 Fundamentals course, as well as get some practice using Python to get the most out of this course. Coming back to what we'll be covering in this course, more specifically, we'll start things off with how to design a machine learning solution. We'll then explore the Azure Machine Learning Workspace. We'll spend time examining the tools that we'll use to work with the workspace, and we'll also discuss how to configure the workspace for our needs. We'll then talk about how to create experiments using the automated machine learning service and how to track model training with MLflow. After that, we'll spend some time on how to optimize our model training using jobs, hyperparameter tuning, and running pipelines. We'll then review how to manage and review models within the service, including how to use the responsible AI dashboard. Lastly, we'll finish the course up with how to deploy and consume the models in a production environment. Before we begin, it's worth noting that this course aligns with the DP-100 certification exam. I, for one, am a big advocate for certification, and I'd encourage everyone to consider becoming certified at the end of this course, and here's why. Let me ask you a simple question. How do you know you've learned everything that you should about the Azure Machine Learning Service? It's not as simple of a question as it seems, is it? So here's the thing. When we here at Microsoft develop a course and a related certification, we actually reach out to the industry and partners and ask, what should somebody working in this space know and what level should they know it at? So you can think of the certification as really being a set of learning goals that your peers in the industry have helped to establish. So try not to think of it as just a piece of paper that isn't really relevant to you, but rather try and think of the certification as your overall learning goal. In other words, if you have learned everything that you should about using the Azure Machine Learning Service, then the certification exam should be easy. If it isn't easy, then you probably have a bit more learning to do. And also, as a side note, I always like to remind our customers that I'd rather have them make a mistake on one of our exams than make a mistake on a real-life project that they're implementing. Ouch. All right, hopefully I've managed to change some minds out there about becoming certified. With that, let's get started with designing machine learning solutions. There are many options to train and consume machine learning models within Azure. Before we start a project, we really should plan some of the time around designing what our overall solution should look like. We need to consider how data will flow from their original sources and the physics of how we'll prepare the data that we'll use for the model training and testing later on. We also need to think about the overall process that we'll use to build our model and make decisions such as what type of model to train or perhaps what services we need to use. We'll also need to think about how our model will be consumed when it's deployed into a production environment. And lastly, we should start thinking about how to best scale and maintain our solution over time, what we often refer to as ML ops, which is short for machine learning operations. Let's get started with designing a data ingestion strategy. Data is the most important input for your machine learning models. You'll need to access data when training machine learning models, and the train model needs data as input to generate the predictions. The catch is that it's extremely rare that we can get the data from the original source system because we usually need to do a number of things to the data to prepare it before we can actually use it for model training. As well, we usually don't want to impose any extra workload on the production systems hosting the original data. So we need to figure out where the original data is hosted and determine a strategy to extract that data efficiently and prepare the data for model training. This is referred to as an ETL or an ELT process. ETL stands for extract, transform, and load, and ELT stands for extract, load, and transform, just reversing the load and transform. This can be done using many different technologies, which we'll talk about shortly. In the example on the slide, you can see the original data is in a JSON format, which is then converted to a table format while doing some preliminary transformations with separating the date-time value. And then the last transformation, we've dropped the device ID column and removed the seconds from the time. Couple of things here. First, it's worth mentioning that one of the biggest advantages of using the cloud is being able to separate compute away from storage, which helps with the overall costing. The benefit here is that we can focus on prepping our data in the storage layer with little to no compute costs. And then when we need to process our data, such as for model training, we can spin up the compute to do the work, and we can have it go away when it's done, reducing the overall cost. We'll be covering compute options later on in the course. As for the data options, you have a lot of options. The three most common options are to use Azure Blob Storage, Azure Data Lake Storage, Gen 2, right, our newest one, or perhaps an Azure SQL database. Azure Blob Storage is the cheapest option for storing data as unstructured data, which is great for storing files like images, text, and JSON, things like that. For data analytics and machine learning workloads, CSV files are one of the most common data formats used, but there are plenty of other formats for storing data within the file system as well, like perhaps Parquet files. Azure Data Lake Storage, or ADLS for short, is a more advanced version of Azure Blob Storage. It can also store text files like CSVs as well as images, but it has some additional features that are useful for data analytics style workloads. ADLS supports a hierarchical namespace, aka folders, and it also supports a more granular permission model, which means it's easier to give someone, or perhaps a service, access to a specific file or folder. Since ADLS is built on top of the Azure Blob Storage service, storage capacity is virtually unlimited, so it's really ideal for storing large amounts of file-based data. Lastly, you can't really go wrong with using an Azure SQL database. This is one of the cloud-based versions of our popular SQL database platform. This can be useful when you want to store data as structured data within a relational database. Definitely a great choice when the data is very structured already and doesn't change much over time. The next thing that you'll need to consider is how the whole process is going to physically go. We typically refer to this process as a data ingestion pipeline, which is simply the sequence of tasks that we need to do to get our data from its source to its destination, which in a machine learning workload is to have the data prepped and ready for model training. It's important to note here that the process is usually being performed outside of the machine learning service. Although we could use the Azure Machine Learning Service to perform those ETL or ELT operations, there are some better tools that are much more dedicated for the job that are readily available to us. The two most common tools that tend to get used are the Azure Synapse Analytics Service and the Azure Databricks Service. The overall process here that's illustrated on the slide is to extract the data from the source, use a service such as Azure Synapse Analytics to perform the ETL, ELT operations on the data, and then output the prepared data to one of the storage services like ADLS, where it can then be consumed by the Azure Machine Learning Service. Since this course focuses on the Azure Machine Learning Service, we won't be getting into the Azure Databricks or Azure Synapse Analytics services here. If you'd like more information on either of those products, you can check out our DP-100 course on data engineering on Microsoft Azure using the link below. Lastly, establishing the ingestion pipeline definitely takes some work to set up, but it's also important to think about the process over time. So what do I mean by that? So think about this. If you processed your data and trained your model today, your model will only know that data that we used today. It won't know any of the data that you might be collecting moving forward, like tomorrow. So we might need to consider a couple of things. How can you streamline the process to add new data without reprocessing all of the data? When do we need to retrain the model? Are we evaluating the accuracy of the model with the new data? Has our new training data drifted? In other words, just because we have new data, it doesn't mean that we need to retrain the model. Data drift is when the new data is statistically different than the older data. So how do we determine that? For now, the point is this. We need to think about this data ingestion process over time. As a data scientist, your focus will be on training machine learning models. Once you have the data you need and it's been properly prepared, you'll need to have sufficient compute to do the model training. To be efficient and cost-effective, you need to choose the appropriate service to train the machine learning model. You need to know what type of model you're training for your situation. You'll also need to understand the requirements of your model so that you can design a model training solution that ensures that the model keeps performing as expected and stays relevant over time. As a general overview of this process, we start with defining the problem. We need to decide on what the model should predict and what the criteria is for it to be considered successful. We need to get the data. Where is the data stored and how do we get access to it? We need to prepare the data for model training. We discussed this previously. We need to clean and transform the data and have it ready for model training. Then we'll train the model. We need to choose an algorithm and hyperparameter values that give us the most accurate model. We then need to integrate that model into production, which means that we need to deploy the model to an endpoint that could be consumed to generate predictions. And lastly, we can't forget that we need to monitor the model so that we know how it's performing over time. Machine learning models are based on algorithms, and those algorithms are broken down into many categories. By the way, I'm sure all the data scientists taking this course are already familiar with this, but it's worth reviewing, especially for those that might be watching this that are newer to the data science field. So, 5 common categories that you really should be familiar with are classification, which is used to predict a categorical value, like what group something belongs to. Regression, which is used to predict a numerical value. For example, to understand the relationship maybe between marketing costs and sales revenue. Time series forecasting, which is used to predict future numerical values based on time series data. And the easiest example of this one would be to predict stock market values. Computer vision models are used to classify images and detect objects in images. An easy example of this type of model would be in quality control systems, maybe for manufacturing plants. Lastly, natural language processing, or NLP. These models are used when we need to extract insights from text. That's a very high-level look at some of the categories of machine learning algorithms that are used to build models. There are a lot more to know about the details of individual algorithms, such as what hyperparameters you should set and what values you should use for them. However, just as a reminder, in this course we won't be going into any of the details on the data science side of things, like the details of how to best use those different algorithms. Our focus is going to be on using the Azure Machine Learning Service. So, speaking of the Azure Machine Learning Service, we happen to have other services that are also capable of creating models, not just the machine learning service. So going from left to right here, we have Azure AI Services, which is a collection of pre-built, the keyword here is pre-built, machine learning models that you can use for common machine learning tasks, such as object detection in images or speech to text. These models are accessed through an application programming interface, API, so you can easily integrate a model with your application. Some models can be customized, or I think a better description is they can be enhanced with your own training data. The upside of this service is that it provides ready-to-go models that can be leveraged in a production environment very rapidly. The downside, though, is that the models are pre-built, right? So aside from being able to enhance some of the models, you can't fully train your own model based on your data with that service. Next is the Azure Synapse Analytics service. Azure Synapse Analytics is primarily designed to ingest and transform data at scale, but also includes several machine learning capabilities. To train models with Azure Synapse Analytics, you can use Spark pools using MLlib. You can also use the integration between the Azure Synapse Analytics service and the Azure Machine Learning service to train models. But that's really an integration component between Azure Synapse Analytics and Azure Machine Learning. Next up is Azure Databricks. Azure Databricks is a data analytics platform that you can use for data engineering and a lot of other data style workloads, and also use it for data science. Azure Databricks uses distributed Spark compute to process your data, and you can choose to train and manage models using Spark and MLlib or other libraries similar to what we would do in Azure Synapse Analytics. You can also integrate Azure Databricks with other services, such as the Azure Machine Learning service to work with your models. Lastly is Azure Machine Learning. Azure Machine Learning is a service that is focused on machine learning and gives you many different options to train and manage your machine learning models. You can choose to work with the Studio for a UI-based experience or manage your machine learning workloads with things like the Python SDK or the Azure CLI for more of a code-first experience. It can be fairly daunting to compare these services. The short version is that the Azure Machine Learning service is the preferred service generally to do machine learning workloads. Azure Synapse Analytics and Azure Databricks are commonly used for other style of workloads, such as data engineering tasks, but have machine learning capabilities. And Azure AI Services is best used when you want to use pre-built models. When it's time to train your model, the most valuable resource you'll consume is compute. It's important to choose the most suitable options for compute, and you should monitor your compute utilization to know when to scale up or down to save on time and costs. Trying to figure out which option best fits your situation is an ongoing process. You'll need to consider some of the following compute options. So, CPU or GPU. CPUs will do the job, and they're cheaper to use, whereas GPUs, right, the graphical processors, will be more powerful and can be effective whenever we're working with unstructured data like images, text, or maybe large amounts of tabular data. The downside to GPUs is that they're more expensive, but since they can usually process the data faster, they usually don't have to run for as long as a CPU. The actual cost will require some experimentation for you. It really depends. General purpose or memory optimized. General purpose virtual machines have a balanced CPU to memory ratio, which is ideal for testing, development, especially with smaller data sets. Memory optimized virtual machines have a high memory to CPU ratio. So these are usually great for in-memory analytics, which is ideal when you have larger data sets or when you're working in notebooks, for example. Services like Azure Synapse Analytics and Azure Databricks offer Spark compute. Apache Spark is an open source distributed processing system used for big data workloads. It utilizes things like in-memory caching and optimized query execution for fast analytics queries that will run against any size of data. When we're thinking of configuring compute, Spark lets us distribute the workload across multiple virtual machines very effectively. Every time you train a model, you should monitor how long it takes to train the model and how much compute is used to execute your code. I would suggest that you occasionally test these different options over time to check to see if you still have the most optimal configuration. Remember that our overall goal is that we need to get our model into production in order for it to be useful. We can't just make them and leave them on the shelf. How we intend to deploy the model can impact how we train it. Once the model is trained, we need to deploy the model to what's called an endpoint. The idea here is that once the model is deployed to an endpoint, an application can send requests over to the model and get a response back with the prediction. Endpoints are simply the location where we'll send the API calls. The biggest decision that you need to make here is whether the model will be deployed to a real-time or to a batch endpoint. Real-time endpoints are used when an application needs to call the model and get an immediate response back with a prediction. Batch endpoints are used when we collect a whole bunch of data over time, and then we want to process all that data in batches. Such as processing the data nightly to generate prediction data. Real-time deployments need to be hosted with continually executing compute. So even when it's not being used to generate predictions, you're still paying for the running compute. Batch endpoints, on the other hand, will spin up compute on demand and then stop after the batch processing is finished. Batch also has an advantage of being able to process the data in parallel, so it can process large amounts of data more efficiently. If your predictions can wait more than 5 to 10 minutes, it might be better to use a batch endpoint since that's enough time to spin up the compute on demand. All right. Let's discuss how to design a machine learning operations or MLOps solution. First, what do we mean by saying MLOps? This is actually a pretty complicated subject. If we take a step back from training a model, we need to ask ourselves things like, how do we move our solution from a proof of concept or development environment into the production environment? Considering that our development environment is typically smaller, how do you ensure that our solution properly scales in a production environment when it has a lot more training data and just simply being consumed a lot more? Can we redeploy our solution to another environment easily if we need to? The overall goal here is to make our solution robust and scalable and answer those questions as best as we can. First, we need to think about separating everything into different environments. A typical approach would be to have 3 environments: development, pre-production or QA, and a production environment. This is best done by having 3 different machine learning workspaces. That way you can separate access to each environment more easily by controlling access to each one with role-based access controls, or RBAC for short. It's also fairly common to separate the workspaces by hosting them within separate Azure subscriptions, which can give you another layer of management and control the environments. When we separate the environments, we need to think about the role that each environment plays. For example, usually we see the dev environment used for conducting experiments for that initial model training and testing. Then we can move the best models over to the pre-prod or QA environment for more rigorous, thorough testing. And then we'll move the approved model over into the production environment where it will be deployed to an endpoint. The point here is that we don't need all of the same services or permissions in all the environments. The production environment, just as an example, is really only used to host the deployed models. so we probably don't need to handle model training and testing or need to grant access to the data scientist. The thing is that your solution and setup will be unique to you, and you'll need to work out the finer details of your solution. You'll also need to consider how to separate responsibilities across your team, as well as consider the iterative approach that happens as we continually improve our models. It's also worthwhile to note here that if you're a data scientist, a lot of this setup will be outside the scope of your role. On this slide, we have an example approach for ML ops. This isn't to say this is the way to do it, it's just an example, but it can help you get started. First, we need to create all the necessary resources for the solution. If you're sticking to the previous example, that means that we'll need to create 3 machine learning workspaces, but we'll probably also need 1 or more storage accounts. We might need multiple subscriptions, and we'll need to make sure only the right people get access to those necessary resources. For example, for the storage, we'll need the data engineers to have access as well as the data scientists. But neither of those roles probably have access to the production environment directly. Next, we'll want to establish the process on how we train and evaluate the model. This will be the main job of the data scientist and most likely being done within the dev environment. We then need to consider how we'll package and register the model, followed by deploying it to the outer loop, which is really about deploying the model to the pre-production or QA environment, so we can do more thorough testing there. In step 5 here, we're finally promoting the package to the production environment where we'll host it in an endpoint and monitor its performance in step 6. Monitoring is also a big part of an MLOps solution. You'll want to monitor the model, the data, and the infrastructure to collect metrics that help you decide on any necessary next steps to improve your solution over time. To monitor the model in production, we usually just examine a small set of data and evaluate if the model is still performing as it should. We should also be evaluating the model for responsible AI issues, such as fairness as well. With respect to the data, our biggest concern is that new data may be introduced with what's called data drift. As I mentioned earlier, it's not new data that drives the need to update a model. It's when the data is statistically different than the old data. As soon as that happens, which is referred to as data drift, then we need to reevaluate our model. Although this isn't usually within the role of the data scientist, we also need to monitor the infrastructure to make sure that we're keeping our costs to a minimum, as well as optimizing performance. Here we can use Azure Monitor to help identify costs, and we can set things like alerts so that we can be notified if any issues might occur. Azure Monitor can help keep tabs on all of the services to help ensure that it's running as it should. To recap, we spent a lot of time on design considerations for an Azure machine learning solution. We started with how to design a data ingestion solution by identifying your existing data sources and how you want to serve the data to the machine learning workspace. Followed by how to design a machine learning solution by understanding the different development environment and compute options. Then we discussed how to design a model deployment solution based on the requirements of how your model is being consumed. And then we wrapped up with how to design a typical ML ops architecture and understand the process from a data scientist's perspective. I hope that this session has been useful to you, and I'm hoping that everyone will continue along their learning journey with the next video in our series where we'll focus on working with the Azure Machine Learning Workspace. See you soon.